Hello everyone. In this video, I'll be solving another problem very similar to the last one, and I'm calling it as 1.20-2 revised. And in this problem, the differences are, let's not talk about the difference. The problem statement is pipe is transporting a superheated vapors. The flow rate is given to be 0.1 kilograms per second. The pipe diameter is 3 centimeters and length is 20 millimeters. So the physical dimensions are given. We know the superheated vapor is entering at 0.1 kgs per second and exiting from the other end. And we also know the pipe is located in a room. The ambient temperature is 25 degrees. The ambient temperature of the room is about 25 degrees. The surface temperature of the pipe is 150 degrees. Because the superheated vapor flowing through, it is heating up the pipe, and the surface temperature is uniform and 150 degrees. That's another assumption we're making it. The temperature drop between the inlet and exit of the pipe is 30 degrees. So between inlet and exit, delta T is given to be 30 degrees. And specific heat of vapors is given. That is 2190 kilojoules, joules per kg, converted into 2.190 kilojoules. So trying to keep the units in check here. And then as a result of the convection, determine the heat transfer coefficient as a result of convection between pipe surface and surroundings. So the way I look at it is the superheated vapor flowing through, the heat from the superheated is transmitted to the pipe. That is, I call it Q loss of vapors. And so the pipe is getting heated, is 150 degrees, and the surroundings are at 25 degrees. That means there is a convection heat transfer is taking place also. And so the two type of heat transfer, one from superheated vapor to the pipe, and the second one is from pipe to the surroundings. And so the relationship is whatever the vapors lost in heat is picked up by the convection heat transfer. The Q loss is equal to Q convection. So three mechanisms are taking place. Now, so that means, but let's start with the problem with the Q loss. How do you find Q loss? Okay, the formula for the heat transfer is mass rate times mass rate into specific heat times T in minus T out. And what are the values? Let's plug those values. Mass is given. Pretty much we know 0.1 kg, and C is given, and delta T is given. So just plug those values. 0.1 kgs per second, I think. Yes, always mass rate is defined, and specific heat is given, converting into kilojoules, 2.190 kilojoules per second. Is it kilojoules per second? Specific heat is what is joules per kg, kilojoules per kg, not second, kg degree Kelvin, and delta T is given to be 30 degrees degrees centigrade. So if you solve this, simplify this problem, it will come up to be 6.57 kilowatts. So that is heat loss, Q loss. We found out 6.57 kilowatts. So now we need to find out Q convection is. So we said Q loss equal to Q convection. Just flipping the page for the second part of the problem, I carried some of the things. We found out Q loss is 6.57 kilowatts, and we know the temperature of the surface is 150 degrees T, and also surrounding is 25. And here we need the surface, because the heat that is on the is radiating or being not radiating, it is being convected from the surface of the tube. So that means we need a surface area of the tube, pi dl, pi diameter times and length, and the diameter length is given, and Q loss. So what is the equation for convection heat transfer? Q loss equal to Q convection, and the equation for the Q convection is specific heat convection times surface area times Ts minus T infinity. So Ts is the surface temperature, and T infinity is surrounding temperature. So, but our interest is to find the heat transfer, convection heat transfer coefficient. So rewriting the equation, H equals Q loss, Q heat transfer, Q by AS times Ts minus T infinity. So plugging those values, you have already, we know Q loss is 6.57, that is the heat transfer part of it, and surface area we said 0.5, 3 centimeter diameter converted into meters, 0.03 meters pi d, and L is 20 meters already given, and it is in meters already. So let me put down the meters here. And the Ts minus T infinity, Ts is given to be 150 degrees minus 25 degrees. So if you simplify this, it comes up to be 20.0278 kilowatts per meter square. Remember the unit for the heat transfer coefficient, it is kilowatts per meter square, but if you put it in watts, in terms of watt, it would be 27.88 watts per meter square, because 1000 watts is equal to 1 kilowatt. So you're converting into, so this is the problem, this is the second part. So this is what the problem is asking for, what is the heat transfer function. I hope you understood this problem, and